Okay, in some sense, this chapter is a big compendium of the previous chapters. Actually, what we've been talking about up until now are various examples of groups. And now we're just going to talk about groups in the abstract. So hopefully we're going to see some properties that are independent of all these different examples. But we'll draw on these examples to understand the properties of general groups. Okay, so you know that groups have an operation, and so we're going to define that in general. An operation on a set G is actually a function from G cross G to G. So what does that mean? It takes for every pair of elements in G cross G, remember G cross G means you have a pair of elements, you can find a unique element that's in G. Now what this is really expressing is kind of like a multiplication table. All right? When you make a multiplication table or an addition table, right, you take a pair of elements and then you get a result. Okay? Now the results have to be in the same set that each element in the pair comes from, so that's why we have G cross G goes to G. So you can think of this example. The elements of G go down the side, elements of G go along the top, and the table is populated with elements of G. Okay? Alright, so here's the general definition of group. A group is a set together with a law of composition, okay, that we've just defined. And the set must be closed under the law of composition. As I said, if you do the operation table, all the elements in the operation table have to be also in the same set as the elements on the sides. There must be an identity element such that for any element A in G, then E composed A equals A composed E equals A. Remember, if we had a group table, there's going to have to be one element in the group table such that if I have E, A, B, C, and so on, all of the entries in this row are going to have to be identical to the entries in the margin. Okay? Because that means E composed D is E, E composed A is A, E composed B is B, and so on. And all the entries in this column are going to be the same as the entries in this margin. Okay? Now I'm not using any specific elements here, I'm just showing in general, if you have an identity element, that's what the group table is going to look like. Okay, so that's the identity. All right, now we also know that there's an inverse element. What does that mean? That means if you go in this table, in every row and every column, there must be an E. There must be an identity element. I must be able to, for any A, I must be able to find some other element, it might be A, it might be B, it might be C, that gets me E back again. And furthermore, if I have C here, A here, that's E, then it must also be true the other way. If I have A here and E here, C here, that must be E. So we have to have, the E's must be located symmetrically in the table. The other elements may not be symmetric, but the E's must be located symmetrically. Okay. Now, the last one is the law of composition is associative. You're familiar with the associative property. That's not easy to see from the table. Okay, you can't, it's very difficult to tell from a table whether you have an associative group law. But the other two you can easily read off the table. Okay. Okay. Special type of group, when you do have the A composed B equals B composed A, I'm say composed or operation or whatever. A, or I can just say AB equals BA. That means that the table is symmetric. That means every element on this side, suppose I have a C here, or for the AB gives me C, then I have to have the AB here has to give me a C. In that case, if you have a symmetric table that's symmetric about the diagonal, that's called abelian or commutative. Right? Now, of course, a group can have infinite or finitely many elements. For instance, the integers has infinitely many elements, but Z5, say for instance, has only a finite number of elements. So that's the distinction between the two groups. Now, every group must have an identity, and in fact, the identity itself does form a group. So we call this the trivial group. And here's your exercise to prove that the trivial group is in fact a group. Okay. Several different examples of groups. So you have to go through and prove all these properties. Closure, And you must also show that there's an identity, that every element has an inverse, and the associative law. Okay. All right. So we've done those things before. So I'm going to pass over this quickly. So you want to show this for various different groups. So just trying to identify this, that this general concept of group does apply to the things we've studied before. Okay. So this is an important remark. You can see that if you have an operation of addition, usually 0 must be included as your identity. But if you have operations based on multiplication, then 0 is not included. This is only when we're talking about groups based on real or complex numbers. In other groups, there's no notion of 0. In the permutation group, there's no notion of a 0. In this special case where you're actually dealing with numbers, then additive groups must have a 0. Multiplicative groups have a 1, but no 0. All right. Now, you can define strange operations that give you a group. Here's an example of a very unusual operation defined between two numbers, and this unusual operation turns out to give you a group. You can go through and show the different properties. In fact, it's an abelian group. You can see in some way that if I exchange the A and the B, I'm going to get the same result here. Okay, so you can go through these proofs and see that this operation defined on this set is a group. And you can see that it's really kind of strange, and the identity, so you're going to have to figure out what the identity is. The identity might not be 1, it might not be 0, it might be something else. You have to figure out what the identity is in this case. Okay, here's some more examples of groups. So you want to go through these examples to understand what's going on. And in fact, these two examples motivate the following general definition. If we have two groups, we can form another one called the product group. And it's denoted this way, G cross H. It's like the cross product or direct product that we've seen before. And every element of G cross H is a pair of group elements. The first element is in G. The second element is in H. And we can define an operation on these pairs as follows. If I have one pair, first element in G, second element in H, and I have another pair, first element in G, second element in H, if I want to operate between these two pairs of numbers, I operate on the first components together, and that will give me the new first component, and I operate on the second components together, and I get the new second component. Okay, so that's how we can define another bigger group that in some sense includes the other two groups. It's called a product group. And this will be important also later. Okay. All right, so here's some exercises. Can you tell from these Cayley tables whether or not this represents a group? Okay, so we're going to go back to some considerations we did before when we talked about modular arithmetic. We found addition tables for Zn and showed essentially that Zn was a group. So now we're going to look at multiplicative groups based on the integers mod n. Now, as we saw before, when we do the multiplicative group, we can't include all of the integers. For instance, if we're looking mod 8, if you can make this multiplication table, and all these zeros are messing things up. 0 doesn't have an inverse, so we're going to have to get rid of 0. And we're going to have to get rid of every row and every column that has a 0. So we'll cross this out, cross this out. Cross out every row and every column that has a 0. So cross this out, cross this out, cross this out. Okay, and cross out the rows with zeros, except for the first one. This has some zeros in it. So if you notice, I'm crossing out all the even numbers. So it turns out if I just take 1, 3, 5, 7 here, 1, 3, 5, 7 here, it turns out that I do get a Cayley table that gives me a group. Okay. And if you remember, we found before that if you have a number that's relatively prime to n, then that number has an inverse in Zn. So all of these numbers, 1, 3, 5, 7, since they're relatively prime to 8, they will all have an inverse mod 8. And it turns out that you get a group. Now we already showed associativity because we're using this multiplication operation mod Z8, which we know already is associative. We showed that in the previous chapter. Now we did this for 8. We can do this for any number n, and that will give us a group. Okay. And here are the exercises that you're going to prove this formally. Fill in these blanks to show formally that the numbers relatively prime to n, less than n, form a group under multiplication. And it actually forms an abelian group, commutative group. Okay. Now, here's another example of groups. Just to show that groups are general, look at 2 by 2 matrices. You know matrices can be multiplied together, and if you multiply two 2 by 2 matrices together, you'll get another 2 by 2 matrix. So the question is, do these matrices form a group? Well, actually, there are two possible operations on 2 by 2 matrices. We can add them, or we can multiply. Okay, so here you're going to investigate whether the set of all 2 by 2 matrices forms a group under addition, and whether it forms a group under multiplication. All right, just to sort of spill the beans. This one works, this one doesn't, but you need to prove that. All right, now this one doesn't. What we're going to have to do is find a subset of 2 by 2 matrices that does work. Similarly to what we did with Zn. We found that Zn itself does not work as a multiplication group, but we found a subset. We found a subset such that all the elements in the subset had inverses. So we're going to do the same thing. We're going to find 2 by 2 matrices that have inverses. Okay? And that's exactly how this is defined. This GL2 consists of the invertible 2 by 2 matrices. Okay, and we're going to try to make this, see if this one is a group. We've already guaranteed that they're inverses. We have an identity, and then it's up to you to continue the proof that this set of invertible 2 by 2 matrices is actually a group under matrix multiplication. Okay. Now here we're getting into more proofs. These proofs are facts that seem pretty clear from the examples that we've done. But to show this in a general way, it kind of warms you up for the type of proofs that you use in general group theory. Okay? So we've said that every group must have an identity element. You need to show here that, in fact, there's only one identity element. There could potentially be more than one identity element. So you have to show that, in fact, the identity element is unique. Okay? And you go through this proof. And I'll just let you read this one. I think this is not too difficult to read. And I think that we actually showed a similar proof in an earlier chapter. Right? So you're going to show, in fact, that if there are two identities, you suppose there are two identities, you end up showing that, in fact, they're the same. Okay. All right, after this, you show that not only the identity is unique, but the inverse of any element is unique. Now, remember that any group element has its own inverse, but it turns out that every group element has one and only one inverse. Okay. Remember, we showed in the functions chapter that there's only one inverse function. If a function has an inverse, there's only one. It's unique. Okay, so that's kind of related to this. Okay, so here's some exercises having to do with inverses. Okay, so here's another important property having to do with inverses. If you want to find the inverse of a product, it's the product of the inverses, but in reverse order. Be careful about the reverse order. Now, if you go back to the functions chapter or the permutations chapter, you'll see that we actually showed this very same thing before. The inverse of the composition of two functions is the inverse of the functions in the reverse order. So here you have a chance to prove this yourself. Okay. Here's another fairly obvious or natural conclusion that the inverse of an element is the element back again. So here you get a chance to prove that. Okay. So these are all abstract proofs that you're proving without reference to any particular number system that the group structure describes. Okay. All right. Okay. All right, here's another proof that in fact groups enable you to solve algebraic equations. That if you have an equation like ax equals b and xa equals b, there's always a unique solution. Now, it's not necessarily the case that the solution to this equation is the same as the solution to this equation. That may or may not be true. But in each case, there is a unique solution. Okay, and you'll go through that proof. And here there's an important note that in the proof, what you end up doing is multiplying by A inverse on both sides, and that's actually a practical technique for solving these equations. It's not just a theoretical technique, it's a practical technique. And of course, this is the same thing that you did in high school. To solve a equation, you divide both sides. Now here, we're a little bit more careful. Instead of saying divide both sides, we multiply by an inverse. And we need to be careful about multiplying on the right or on the left. You need to be careful about that. Okay, so some exercises having to do with that. Okay. All right, so we use that to show the law of cancellation. If ax equals ay, then x is equal to y. Okay. And that's similar to what's above. Okay. Now we define another notation, the exponentiation notation. If you have a group element and you operate on itself n times, we denote it this way, g to the n. Or if you take the inverse and then you operate it on itself n times, you call it g to the minus n. Okay? And then here you have a chance to prove the exponentiation laws. These are the usual exponential laws that you know and love from high school algebra. Okay. Now, one thing to note is that that may be a little confusing, that in additive groups, when you, instead of writing g to the m, when you're operating m times or n times, you're actually adding m times or n times. So it's quite interesting that the exponentiation laws generalize to these additive laws in the additive group. So be aware that g to the m in an additive group is written as mg. Okay, g to the m means you operate m times on m copies of g. If I operate m copies of g in an additive group, that means g plus g plus g dot 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 plus g m times. Okay, I'm still operating m on m copies. Okay, and I can write that as mg in an additive group. Okay, so we'll stop here.